Good morning, good afternoon, good evening, depending on where you are. My name is David Wei. I'm the CTO of SONT Technologies. Today, my topic is WDM technology-based solution for 5G fronthaul connections. So just one high-level introduction on the background. Many people have been familiar with these 5G telecom network applications. There's three main applications. One is the enhanced mobile broadband, ultra reliable and low latency communication, and the massive machine type communication. And to support these three types of application, we need a robust, reliable, high-speed 5G network. In this page, I'm showing one sample architecture of a 5G network, which includes three different portions. One is the fronthaul portion, and then depending on which carriers, some carrier might add the mid-haul connection, and there's the access layer, aggregation, core, and all the way to the data center part. And for the 5G base station deployment, according to the estimation, there's different kind of numbers there. Compared to the 4G stations, some carriers estimate to be 1.5 times of the total number of 4G stations, and some carrier can go as high as 3x. Regardless, there's a huge amount of 5G base stations ahead. And on top of that, for these connections, for this station connecting to the BU, each channel, the bandwidth is getting higher as well. Compared to the 4G, 10G per channel in the 4G LTE, mostly in the 5G, people talking about 25 gig eCPRI connection per channel. And of course, from a fronthaul portion, there's a wide range of link distances from 10 up to 10 kilometer to 15 kilometer or even 40 kilometers. While the 90% of that link, as of today, we see as a 10 kilometer, while the rest of about 10% covers from 15 to 40 kilometers. On top of that, people also talking about adding a function, adding the operation, administration, the maintenance, in short, is OEM functions into the fronthaul connections. So at the early stage of a 5G deployment, of course, we are still in the early stage right now. Some carriers are using just leveraging on the 4G LTE's methodology in terms of fronthaul connections. In the 5G, people call a AAU on top of the tower, and there are 3 AAUs on each towers, on station tower, and each AAU has a 2 by 25G connections. So back to the DU, the total connection for 5G network fronthaul, it's a 12 channels or 12 modules. And if using the so-called gray light, such as LR or ER connection, that needs about 12 fibers for connecting each station to the DU. And of course, this is with a duplex connector type. Some carrier use the BiDi technology. This can reduce the fiber deployment by 50%, which is equivalent, for each station, there will be 6 fiber. That is through the simplex connectors. And of course, this type of way of connecting AAU with the DU is only for smaller scale centralization, the CRAN, in terms of CRAN. And there's another way of connecting that is using the OTN type of equipment. Of course, OTN has its own benefits, such as the full OAM functions. However, it's very expensive. Considering 5G network, especially the Fronthaul, takes up the main capex consumption there, a new way needs to be found out or need to be to address the cost, and in the meantime, the connecting quality issues. So on the new solution, especially for the CRAN centralization architecture, there's the medium scale CRAN, like some people use the 120 core fibers. There's also a large scale connection. It's even up to 240 core fibers for connecting the in the CRAN centralization methodology. And in that way, people are looking at one fiber for one station connection, which means if it's 12 channels, all 12 channels will need to go through one fiber. Then that leaves us only one solution. There is a WDM type of a technology. This will help reduce significantly the fiber cost. And on top of that, if we can add just enough OAM functions, not necessarily the full OTN type of OAM function, but just enough so-called lightweight OAM functions, then it could be a solution there. So what we have been doing, and together with the industrial partners, we are working on WDM wavelengths, WDM technology-based Fronthaul connection. And from the there are two key points. Key point one is the wavelength planning. As we know that ITU-T G.Metro has been standardized using the DWDM type of technology. That's a very nice technology, but it's kind of expensive compared to what we have been doing recently. We focused on the O-band. In the O-band, there are three types of wavelength grade which are being working on. One is the coarse WDM, like what we such as used in the data center connection, the CWDM4. There's 4 channels. We just need another 2 channels. However, that's a challenge as well. On top of that, on top of the CWDM4, we added 1351 and the 1371 nanometer. A second way of WDM wavelength planning is called median WDM or MWDM. The idea is that fully leverage on CWDM grade and using some methodology, either it's a thermal tuning or a fixed wavelengths, just to pull the 6 CWDM wavelengths to the longer part and the shorter part by plus minus 3 nanometer or slightly more or less than that. The third way of utilizing the O-band spectrum is the LAN WDM. As we know that 400G LR8 has already been standardized by IEEE. There is a relatively matured industrial supply chain for supporting this wavelengths. So the idea is that to have a 12 wavelengths, we add another 4. Of course, this is working together with several, not just by us, but with other companies as well. Adding another 4 wavelengths One is a 1269, the other one is 1291, and also a 1313 and 1318 as well, just to have an equal spacing 800 gig between the neighboring wavelengths to make it a 12 total. So just a little bit more information here. This different type of WDM technologies currently with a different level of supply chain maturity. Of course, the cost is different as well. And also there's the factor of link budget. And for the 25 gig CWDM to really have a 12 wavelengths, what we have now is actually the 6 wavelengths from 1271 to this is the 1371, total 6 wavelengths. As a DML laser, it's a low cost. The main challenge for this one is at the longest wavelengths, there's a dispersion penalty, which is 4.5 dB, around 4.5 dB. That was measured, and of course. And the maturity-wise, the supply chain maturity-wise, the first 4 wavelengths are mature, and the 1351 and the 1371 are in a small volume shipment right now. And to make a CWDM 12 wavelengths, if we have another 6, it will be 1471 and 50 to 1571. This has to be using an EML laser to relieve the dispersion limitation. Of course, the cost will be high. At the moment, it's a sample stage. And on the bottom, what I show is the LAN WDM and the DWDM as well. DWDM, 25 gig DWDM, it's still at the sample stage at the moment. The 25 gig LAN WDM using a DML laser, and it has a low dispersion penalty. Wavelength planning is the key point 1. The key point 2, as I mentioned early on, is the OEM function for the Fronthaul. We know that in the 4G, it's either the passive or using an OTN is kind of an expensive methodology to address the Fronthaul issues. If we say people will estimate the Fronthaul could take us from 60 million to 90 million units, transceivers to be shipped there. If it's too expensive, it's kind of a prohibitive for the carrier to deploy. So what we have been working on is this scheme 3, which is called, another way is called it, it's a semi-active open WDM. It's a 1 fiber for 12 channel. The cost is relatively low compared to the OTN, but it's still higher than the passive WDM technology, as you can understand. And it also can provide protection, which I will show later on. And in the deployment wise, it's on the AAU side, it's a passive. So what you can see is just the passive WDM box here. And on the DU side, there's active WDM management associated with that. And we add the lightweight management functions through the channel. So on the transceiver side, what I'm showing here is for the 5G Fronthaul transceivers, WDM-based, different types of wavelength grade, the cross WDM. For the 6 wavelengths, the first 6 wavelengths we have now, it's already in the volume shipment. It works for eye temperature range, of course. Support up to 10 kilometer using the uncooled lasers. And we are developing 1471 to 1571 nanometer 6 wavelengths right now. So to make it the full 12 wavelength CWDM series. It has a DDM support, of course. And for the LNWDM, as I mentioned, 800 gig spacing, that one. It supports eye temperature as well. It has a cooled lasers inside, as you understand, because the spacing is too close. To work at a full temperature range, we have to use an cooled methodology. And it has a DDM support. We have two versions. One is the 10 kilometer, which uses the ping, and actually this is a DML. And then the 30 kilometer with an APD receiver plus the DML. For the median WDM, the MWDM, it's 12 wavelengths. We can ship right now in volume, industrial temperature, supporting up to 10 kilometer with a ping and a DML laser. For longer reach, like 15 or even longer, we will either have to use the APD or EML or both of them. And that's a DDM support as well. The DWDM is a C-band. It's on the standard C-band grade. We can support both the 10 kilometer and the 15 kilometer. These are the transceiver series we are shipping right now. On top of that, we provide the MUX and DMUX boxes to make it a full solutions for the, for example, the CWDM. We have a 6-channel or 12-channel versions. For the LAN WDM, it's 12-channel versions. MWDM is 12 channels as well. And for the OEM functions, adding to these transceivers, this one I can spend a little bit more time to explain. And as previously, all this module is just simply an electrical optical signal converter, right? Because it's a kind of a EO and a OE conversion. It's doing that, doing it's a basic physical work. For this one, OEM, we add functions to those transceivers to make it smarter. To explain that, it's kind of just adding a small amplitude modulation at a low frequency out of band OEM signal on top of the main optical signal, so that this signal carries, these OEM signals carry the module information, such as the all this DDM information, like optical power, the voltage, the temperature, and also such kind of the information will be carried with this OOB OEM message. It will be sent together with the main signal from one end to the other end, will be dissected by the receiving end, and then it can be retransferred back to the channel. And doing that is actually the module. From my understanding, it's not just a simple OE signal converter. It becomes smarter. It can be used to remotely control the transceiver on the other side. For example, if the transceiver is sitting on the tower, right? Because we probably don't need to send the people there to check out if there's an error, if there's a problem. We probably can just sit in the building, and then using the transceiver on this end, send the control signal through the main channel, of course, in the form of OEM message to the receiving end, And then the receiving transceiver will be able to analyze the command sent from the BBU and then do the work correspondingly. So this is the idea here. And then the transceiver not only doing the physical layer work, it also doing the link layer. And also, of course, it has to follow some kind of a protocol to be able to achieve these functions. And then this map, this diagram here, just the idea of doing that. And of course, we can put in a photodiode monitor here, and then monitor the channel here. This one channel, this one monitor can monitor the two modules information here. If we add the so-called reflection functions on the transceiver. And on the bottom, on the right bottom corner here is actually one of the equipment we have developed for achieving this OAM function to control. This one will be sitting in on the BBU side. On the left-hand side is the control interface. We have to put it in English versions here. Right now, it's still non-English version. So on top of the OAM, of course, we can also add the line protection functions here. In short, it's OLP. The idea is pretty simple. It's for the fiber, if there's two duplex fiber, one is used as a main for transmitting back and forth the signals from 12 channel. The other one is used as a spare. Just in case, of course, we will have the keep monitoring the channel. If there's a channel failure, this equipment here, active marks here, it's the one I just showed the photo. We'll be able to switch to the communication to the spare part. And so there's ongoing standardization activities just happened this year. One is within the ORAN Alliance, which is I think it's in the summertime setting up the X-Hall Transport Working Group. As of today, there are already 33 plus companies joined the working group. The targeted goal is to developing series of standards, including WDM-based Fronthaul network control and semi-active MWDM, LAN WDM as well. We expect the first draft of WDM specifications to be released early next year. Another major activities is on the ITU side. There are industrial partners that are driving the MWDM standardization in the SG15Q6. And during this year's July meeting, the 12 wavelengths O-band WDM for Fronthaul is the first time proposed. And then during the this year's September meeting, the G.OWDM standardization process was formally started. And then the wavelength range was from 1260 to 1380 nanometer was chosen. And this is we believe this is a significant milestone for O-band to be used for the O-band WDM-based Fronthaul connections. So at last, it's a new open WDM architecture for the Fronthaul connections. There's I think the three news. One is the management on the management division part. It's a separate wireless and the transport management domains. The second is decoupling. Decoupling the transceiver from the AAU, which helps lower the capex. And of course, the maintenance to lower the cost. With this low cost, flexible light OEM mechanism, it helps to lower in the OPEX as well. Just think about it, we can remotely manage, monitor, and control the transceivers on top of the module, on top of the wireless tower, instead of sending folks to climbing up the towers to do the work. Okay, thank you. You are welcome to visit our ECOG booth number. ECOG booth, the number is 393 and 395. Thanks.